So let's start interprocess communication. Interprocess communication is a key component that makes it easier for process to communicate and coordinate their actions. We actually seen them in the week that we first talked about processes. If you remember from that course, it basically represents the collaborative way of information sharing between processes. So first kind of interprocess communication is message passing. Interprocess communication messaging with processes send and receive messages and queue messages for processing in an arbitrary order. It is characterized by two essential primitives, send and receive. They facilitate the sending and receiving of information by acting as digital ambassadors. Okay. So processes can send messages by using the send operation, which gives them the choice to transmit the message with a specified destination, okay, or without specified any destination. On the other hand, receive action acts as the receiver, waiting patiently for any message, giving the option to accept messages from any source or wait for messages from a predetermined source. So all processes can exchange information through a communication message queue. Between them, a communication link is established. If a link already exists, no need to establish it again. And the sending process places a message via message passing module onto the queue, which can be read by another process by using message passing module in the other side. Okay. So messages actually can have one or two Unix sizes, variable or fixed. And in its most basic form, a message consists of two main parts, header and the body. This division offers a well-organized structure that separates necessary control data from the message's actual content. So messages in the Unix environment are known for not having an identifier. Instead, they only include message types. So this minimalist approach simplifies the message structure in Unix environments. Important parameters that determine how the method of communication operates are included in the control information of a message. This may include instructions on what to do in the case that buffer space runs out, or sequence numbers to keep things organized and consistent, and the prioritization of messages. So all these components work together to make interprocess communication precise and trustworthy. Additionally, the technique of message queue can be first in, first out approach. It is important to remember too that queuing disciplines can go beyond basic first in, first out approach and include some, I don't know, maybe priority techniques to handle the different importance of messages. So in summary, in this discussion, we saw a common method for interprocess communication, message passing. Okay. So it permits communication between processes either running on the same machine or throughout a network or distributed system. In the information exchange, actually there are two types of message passing, synchronous and asynchronous. So let's review the basics of synchronization in message passing. Processes may or may not be blocked during message passing. Blocking is synchronous. A blocking send means that the sender waits until the message is received. And a blocking receive means that the receiver waits for an available message. Non-blocking is asynchronous. So a non-blocking send allows the sender to continue, and non-blocking receive permits the receiver to obtain a valid message or yield without any waiting. But typically for a sender, it usually prefers to be non-blocking after message passing to accommodate sending messages to different processes. And a receiver usually prefers to block links, since after it receives an information, it needs to use this information for further execution. But we can say that there are basically three most popular combinations. The first one is blocking send and blocking receive. The second, non-blocking send and non-blocking receive. And the third is non-blocking send and blocking receive. Actually, the last one is the mostly used one, and it's the common scenario, especially in server processes, providing services or resources to clients. Okay, so let's look at link capacity. Yes. So one of the most important factors in deciding how messages are handled in our system is its capacity, which is usually enabled by a queue connected to the link. There are three different ways to create this queue, and each one affects how sender and receiver communicate. So the first one is zero capacity. So it's like a rendezvous-like situation. It resulted when there is a zero capacity in the queue, meaning that no messages may be sent or received. In this situation, the sender must wait for the receiver. The second kind is unbounded. No, let's first look at bounded capacity. Yes. Bounded capacity. So in bounded capacity, the queue can hold up to n messages because of its finite length. In this case, if the queue of the link fills up completely with n messages, the sender will have to wait. In the third case, we have unbounded link capacity. And it denotes an indefinite queue length so that the sender never has to stay waiting. Overall, the implementation method selected, zero, bounded, or unbounded, determines the sender-receiver interaction dynamics. There are also several ways to initiate communication link, direct communication or indirect communication. In a direct communication scenario, specific process identifiers are used for source and destination. But this can be challenging when the source cannot be known in advance, such as in the case of print server. In contrast, indirect communication involves sending messages to shared mailboxes or ports, providing a more convenient approach where senders place messages in a place and receiver picks them up from there. Let's look at direct communication in more detail. So the process that specifically identify one another for message exchange are said to be direct communication. In this paradigm, the sender sends a message to a specified process represented by the letter P in the example by using the send operation. On the other hand, the receiver uses the receive operation to get a message from a specified process as seen in receive queue message, where Q is the sender. Okay. So the communication link between processes is automatically established in direct communication. And each link is connected with exactly one pair of communicating processes. It assures one-to-one relationship. There is only one link between any two processes, resulting in a clear and deterministic communication structure. While the link might be unidirectional, it is most likely bidirectional, providing two-way communication between the processes. This technique to direct communication provides a simple and straightforward method for processes to communicate. So now let's look at what indirect communication is in detail. Indirect communication is a type of interprocess communication in which messages are sent and received through shared mailboxes, which are also known as stores. Okay, so each mailbox has a unique identity, and processes can only communicate if they share the same mailbox. This strategy offers levels of abstraction, which simplifies process communication. So the properties of the link in indirect communication include the following. So the link is established only if processes share a common mailbox, and a single link can be connected with several processes. As you can see in the figure, we have many processes from one to n. Also in the receiver side, we have multiple processes. Each pair of processes can share many communication links, and it enables flexibility in the communication topology. The link itself can be unidirectional or bidirectional, allowing for one-way or two-way communication between processes. Indirect communication operations include creating a new mailbox, sending and receiving messages through this mailbox, and destroying the mailbox when it's no longer needed. So primitives or fundamental operations are defined for indirect communication too. For example, send a message denotes sending a message to mailbox A, whereas receive a message denotes receiving a message from mailbox A. So in this case, this is the idea of mailbox. So mailbox sharing presents an interesting challenge. For example, when multiple processes such as process 1, process 2, and process 3 share the same mailbox, and process 1 sends a message while process 2 and process 3 receive it, we want to determine who received it because it's a critical decision. So there are several solutions for it, such as limiting a link to only two processes, or allowing only one process at a time to execute a receive operation, or allowing the system to randomly select the receivers while notifying the sender without the chosen receiver. Okay? So let's examine mailboxes and ports. As I said, they are essential components of indirect communication. Mailboxes can be private or shared. In private mailbox, a mailbox can be dedicated to a specific sender-receiver pair, and it established a private communication channel between those two protocols. And this ensures a direct and exclusive communication. In the shared mailbox, a single mailbox can be shared by multiple senders and receivers. Multiple processes can contribute messages to the same mailbox in this scenario, and multiple processes can also extract messages from it. The operating system may allow the use of message types to facilitate message selection. And a port is simply a special mailbox that can be used by multiple senders. Okay, from one to n, we have n senders, but port is connected to a single receiver, Q1. So significant use of port is seen in client-server architectures. In this case, a port is linked to the receiver, which is usually a server. Okay, and also in client-server applications, so the message to the shared port can then be sent by multiple senders. So usually we call them as clients. So overall, in client-server applications, this configuration streamlines interaction and increases efficiency by actually simplify the communication